Okay, so I've made up a question here for you that has both conditional probability and independence. And let's work through this, and then I'll look at number 12 from your homework, and we'll work through that as well. Okay, so you've got a normal card deck with 52 cards, and we're going to let E be the event that the card is black. And we're going to let F be the event that the card is a face card. We'll consider jacks, queens, and kings face cards. So let's find two conditional probabilities. The probability that we have E given F, or the probability that we have F given E. And then we'll answer the questions, are E and F independent? Okay, now, intuitively, this one is difficult to do. Unlike a nice little chart that helps us to do things intuitively. So when you don't exactly see how the conditional probability is going to work, the best thing to do is go to the formula for the conditional probability. So we can find the probability of E given F by using the formula, and it's always going to be the intersection of the two events in our E given F notation. So E and F, or I think I can find my intersection symbol, maybe. So E intersect F, and then on the bottom will always be the probability of the second one in the notation. So the probability of F. All right, so in this instance, let's figure out what the probability of the intersection is. Okay, so if we think about all of the cards in the deck that are both face cards and black, well, there is a black jack, queen, and king of spades. And there is a black jack, queen, and king of clubs. So that's 6 black cards out of the 52 in the deck. So there's our intersection, our top probability. On the bottom, the probability of F, the probability of a face card. Well, we have those black face cards that we were just talking about, but we also have hearts, a jack, queen, and king of hearts, and a jack, queen, and king of diamonds. So that's 6 more cards. So there's 12 out of 52. All right, now, if we remember that this fraction right here, this fraction bar right here is division. Our rule for fraction division is to multiply by the reciprocal. So this becomes 52 over 12. And the 52's here will cancel out, which gives us 6 over 12, or a probability of 1/2. Now, let's go to B. Again, let's use the formula because it's not necessarily intuitive. Again, the formula calls for the intersection of the two events in the notation. So again, the intersection of F and E. And when we're talking about the intersection, it doesn't matter what order we write them in. So it'll look just like this, E intersect F. And I hate it when it does that. Here we go. And then the bottom this time, though, will be the probability of what's second in the conditional probability. So E. Well, I hate it when it does that, but there we go. All right, so we already did the probability of E intersect F. That was 6 out of 52. Now let's do the probability of E. So the probability of getting a card that is black. Well, we have black spades. There are 13 of those in the deck from the ace all the way to the king of spades. And then we have the black doggy feet or clovers, again from ace all the way to the king, and there are 13 of those. So there's 26 total black cards. So this will be, and I didn't mean for it to pop in the middle of the question, 26 out of 52. Now again, just like the last one, we can tell that when we flip the fractions, the 52s are going to cancel out. We're going to get 6 over 26, which is going to reduce to 3 over 13 as our probability. Okay, now let's go to the idea of independence. there are cases where independence is intuitive. For example, if I have Joe working alone without any aids other than perhaps his calculator in a room on a problem, and I have Samantha working in another room on that same problem, assuming they don't have phones or something, they are working independently. But most of the time, independence is not intuitive like that, and we have to do the calculations to figure out whether or not two events are independent, whether or not they have some influence on one another or not. All right, and if they're independent, they don't have an influence on one another. There are two ways to check for independence. One of them is to use the conditional probability. So that would be to show that this equation is equal to, or this side is equal to this. So notice that the first part of the conditional probability is equal to the first part without any condition. So in other words, F doesn't in any way change the probability of E. Now that's one, or we could do the reverse of that. Oops. So in other words, either one of those would prove that it was independent. Or there's a last way. We can show that they're independent if the intersection, so if the intersection is equal to the two probabilities multiplied together of the two events. All right, so really three ways here that we can think about independence. And we can show that if one of these is true, and we only have to show one of them, if one of these is true, they are independent events. Now, I suspect that they are not, but let's find out. And let's do it all three ways, just so you understand the concept here. Okay, so E given F. Well, we already figured out E given F, and it was a half. So the question is a half equal to the probability of E by itself? Well, we actually figured out the probability of E by itself in the bottom half of this equation. It was 26 over 52, which, if we think about 26 over 52, reduces to a half. So hey, that's independence. Okay. Now we could do the other equations if we want. We'll get exactly the same result. So let's see, the probability of F given E, that was 3 out of 13. And the probability of F, we actually did up in, so the probability of F, we did right here. It was 12 out of 52. And notice that if we were to reduce 12 out of 52, dividing both 12 and 52 by 4, we would get 3/13. So again, we get independence through that formula. Now, the last one, the probability of E intersect F. Well, we know the probability of E intersect F is 6 out of 52. And then the probability of E times the probability of F. Well, let's see, the probability of E when we got it up here was 26 out of 52. I'll put this in parentheses. Times the probability of F, which is 12 out of 52. And this may be one where we want to do it with decimals, just so that we don't have to reduce that horrible fraction, or we can reduce them first and see if it's not as bad. Let's do that. Let's see, 6 out of 52 reduces to 3 over 26. And then let's see, 26 over 52 reduces to 1/2. So let's just reduce it before we have to multiply. 12 out of 52 reduces to 3 out of 13. And of course, let's see, as we finish that off, that's going to give us 3 out of 26 on that right side. And there we have them as being independent again. And as I said again, independence is not necessarily intuitive. And so we have to go through one of these 3 formulas. And notice any one of them will prove independence. So it doesn't matter which one we use. Okay, so let me go to the homework problem, number 12 that you asked about. And okay, so it's this one. A math class contains 8 females, 3 of whom speak French and the rest speak only English, and 11 males, 2 of whom speak French and the rest speak only English. And we have 2 parts. A student in the class is chosen at random. If you're told the student is male, what is the probability that the student can speak French? Okay, now, anytime we see the words given or if, we should immediately think this is conditional probability. And the if or the given part is going to go after the line in the notation. Okay, so if the student is male, so we're going to have after the line the male, and we'll call it M. And then what is the probability the student can speak French? French will go before the line in our probability notation. So I'm going to write down a few things just to help us out here. We had that there were 8 females, and of those 8, 3 spoke French, which meant that 5 were left over for English, and 11 males, and 2 spoke French, which meant that 9 spoke English. Okay, now going back for a second. So we had if the student is male, so that's after the conditional probability line, we'll have M, and before that conditional probability line, we'll have French, F. So we're going to have, we want to find the probability they speak French given they are male. All right, so we can do this the intuitive way, or we can do this using the formula. Let's do formula first, and then I'll talk about the intuitive way. The formula says we need the intersection of these 2 events, F and M, on the top. And actually, let me go back because I noticed this is confusing. There are 2 F's. Let's call the females W for women. Because we've got French here, so otherwise they'll get a little confused. And then on the bottom we'll have the probability of males, the second item, the item that's after the given part here. Okay, so the probability that we have someone in our group who is both male and speaks French. Okay, so if we look for people who are male and speak French, there are 2 of them, and that's out of a total of 19 people. So 2 out of 19. So there's the top of our fraction. All right, now we want the probability that someone is male. Well, there are 11 males out of our 19 people. 11 out of 19. And of course, if we use fraction, division changes into multiplication, this flips over. Or if we want to take our shortcut, we realize the 19s are going to cancel, and this becomes 2 over 11. All right, now let's do it intuitively. One way you can think about it using the language, the probability of getting someone who speaks French out of the males, given that we have a male. In other words, our sample space suddenly changes to males because we're given males. So our sample space changes to males. Out of those males, how many speak French? All right, so 2 out of our sample space 11 of males. All right, now let's do the second one. Going back to the example, the first student is placed back into the class, which means essentially we're resetting back to the original numbers when we place something back in. So really we're back to the same kind of problem we had in A, perhaps. All right, so another student's chosen at random.